So the title of my talk is Flexibility in Contact-Free Manifolds from Contactomorphisms to legendrian nodes. This is joint work with Eduardo Fernandez and Francisco Presas. It will cover part of the topics in the paper recently uploaded to archive with code, the one you can see in the screen. So I'll start from the very beginning, which is introducing contact-free manifolds. So first, we need to introduce what a K-distribution is in a smooth manifold. So a K-distribution is a smooth K-rank bundle of the tangent bundle of the manifold, or equivalently, we can say that there exist pointwise linearly independent local vector fields from x1 to xk, such that they linearly span the delta, which is the distribution. So I've depicted here an example, which is a true distribution in R3 given by the kernel of DC, which is given by this family of planes, all of them parallel to the plane given by the C coordinate equals 0. In fact, this is a very particular kind of distribution that looks very nice, even locally, because it's very linear, as you can see. This is what we will call integrable distributions, but there are certain distributions that don't look so well, as we will see. So let's start defining first what an integral submanifold is for certain distribution. So let M delta be a manifold equipped with a distribution, which we say that the submanifold M inside M is an integral submanifold if for every point in the submanifold, the tangent space lies inside the distribution delta. So in the example above, the one given by the distribution defined by the kernel of DC, the submanifolds can be taken to be at each point Q plus the span of the vectors partial x, partial y. In fact, these submanifolds coincide with the distribution itself, and they are integral. Let's go now defining what integrable or non-integrable distributions are. So a K-distribution delta is said to be integrable or non-integrable if for every point P in the manifold there is or there is not an integral K-dimensional submanifold N inside M passing through the point. In other words, containing the point. So here I've depicted delta in red, which is the distribution, and you can see here N, which is in color green, the submanifold passing through the point P. And this must occur at all points in order the distribution to be integrable. If at any point it occurs just the contrary, I mean, at any point we cannot find such an integral submanifold, then we will talk about non-integrable distributions. From now on, we will focus on non-integrable distributions, since we will focus especially in contact distributions, which are a particular instance of such kind of distributions. So a remark to be done is that non-integrable distributions, they must look very twisted, even locally, because as we said, they don't admit integrable submanifolds. So this must be encoded by saying that locally they cannot look linear. In a sense, they must contain some abstraction to these submanifolds to exist. So let's define now what we understand by a contact-free manifold. Sorry. Okay. So a pair M, psi is a contact-free manifold if M is a smooth threefold and psi is a non-integrable hyperplane field. In other words, psi is a two-plane family or a two distribution which is non-integrable. So let's go with some prototypical examples. The first one is the distribution given by the kernel of dy minus cdx in R3. And it looks like the one in the picture. So as I mentioned, this distribution is non-integrable. And as you can see, if you go along the lines, the distribution is turning. And in fact, you can see some of the directions. The one horizontal to the screen is pretty clear. And what this encodes is, as I mentioned, that no integrals of manifold can exist. This is maybe visually more clear in the second case, which I present here, which is R3 with the distribution given by the kernel of dc minus r squared d theta. This is in cylindrical coordinates, and d theta is the angle coordinate. So if you regard there, you can see that at the origin, you have a plane, and if you go in any radial direction, distribution is making some turns in all the radial directions. And again, this is encoding the fact that no integrals and manifold can live there. So an important feature of contact topology is the lack of local invariants, since all contact structures look locally the same. This will be described by a theorem I'm going to state later, but it's just a remark that it's important to be done. So let's start defining what a contactomorphism is. So a contactomorphism, it's just a transformation of the contact structure that preserves the contact structure. It's what one would expect to be. So we say that a contactomorphism between two contact manifolds, M1 psi1 and M2 psi2, it's a diffeomorphism phi between M1 and M2 such that the push forward of psi1 equals psi2. So we state now the Darboux theorem for contact threefolds, even if it works for higher dimension, since we are focusing in the case of three-dimensional manifolds. I'll state it for three manifolds. So let M psi be a contact three manifold and take a point in the manifold. And then there exists a small ball centered at the point with local coordinates x, y, z, such that the distribution looks like the kernel of dy minus cdx. And so what this is saying is, okay, if you take any point at any contact distribution, you can always find coordinates in such a way that the distribution looks like a local model, that it's the standard contact structure, sorry for moving the screen, which is this one. So this is the reason that we made the remark before, saying that this means that no local invariants exist for contact manifolds. So if you are interested in finding invariants, you may look for global invariants. So let's go now with the second part of the talk, which concerns legendrians and manifolds. So let's start defining what we understand by a smooth or a legendrians and manifolds in R3. So definition, a smooth embedding from S1 to M3 is called a legendrian if the derivative lies inside the distribution for any point. In other words, if it's integral for psi. Since, as we mentioned, R3 with the standard contact structure is a local model for every threefold, let's focus in this case and let's try to describe legendrians and manifolds for this distribution. So we take gamma of t, we parameterize it by x of t, y of t, and c of t. And so it's legendrian if its derivative, which is given by x prime, y prime, c prime, lives inside the distribution for any point. This is just by definition, but if we take a careful look here, since this is the contact structure, it's given by this kernel, this means that this equation reads as y prime of t minus c of t x prime of t equals 0. And whenever x prime of t is not 0, this tantamounts to saying that c of t can be expressed as the quotient of y prime of t divided by x prime of t. So in R3, with the standard contact structure, we have two preferred projections, which have their own name. So the first one is the front projection, which takes SYC and it projects it to R2 just by forgetting the third coordinate. And the Lagrangian projection does the same, but forgetting the second coordinate. So why are these projections important? Okay, the reason is that we are working in the three-dimensional space, but we are projecting to a two-dimensional space. So we are losing one dimension. And so a priori, it would seem that maybe we are losing some information. but this is not the case since we can recover the third coordinate in an easy way. So let's take a careful look and let's see how we can recover these coordinates. So for the case of the front projection, since we have the formula, okay, C of t equals y prime of t divided by x prime of t. If we look at the picture, this formula just tells that we can recover the c coordinate by computing the derivative at any point in the projected curve. So, for example, if we take here this derivative, and let's say, I don't know, it's whatever, -3 or +3, then what this is saying is that if we try to lift it, then the c coordinate will equal 3, for example. So it's saying that we can recover the missing coordinate just by differentiating. And as you may have guessed already, since we can lift from the front by differentiating, how can we lift the curve from the Lagrangian projection? Well, just by integrating. So we have here this formula, and just note that this integral here is the Euclidean area in the xc plane. So what it's telling you is that you can recover the missing coordinate just by measuring the enclosed area by the curve. So the remark here is that if you take a Lagrangian projection of gamma, it has enclosed area 0. Why is that? Okay, since gamma of 0 equals gamma of 2 pi, because it's a closed curve, and you have also this formula here, then this integral must be 0. But this integral is precisely the enclosed area, which is signed. So in the example I've depicted, the lobe here with area A must compensate the area enclosed by the other lobe. And as I said, these are signed areas, so they go with certain orientation. So, okay, let's go with this big question in the field, which is understand the topology of the space of Legendrian embeddings in terms of the space of smooth embeddings. This is a very big question in the world of contact topology. So for the case of Legendrian embeddings in R3, it was very well understood for the level of connected components, but not so much was known for higher homotopic groups. So let's take a look. So if we take the natural inclusion for the space of Legendrian is in S3 with the standard contact structure that looks like the formula I've written there. And we consider the natural inclusion into the space of smooth knots. So we can pose the question of how are they related? Well, also at the level of certain homotopic groups that we have an injection, a surjection. So let's start with the pi knot case. Is gamma surjective? In other words, can any smooth embedding be realized by a Legendrian one? The answer is yes. Any smooth embedding can be realized by a Legendrian. Let's prove it. Work in the Lagrangian projection. So we take a green smooth embedding that, well, we take a realization of it that projects generically to the xc plane. And so what we do is the following trick. We approximate it just by adding loops in this fashion. And we add as many loops as we need. The trick here is that we can, as you remember, the possible obstructions are the area not being 0, and the crossings should go the way they should go. So the trick is, okay, then you can take a loop, like the one here, A, and just increase it or decrease it in a certain way, in such a way that you are approximating the green embedding. And since you can add as many loops as you want, then you are done. So this is for surjection. But the next question is, okay, it's surjective, but is it injective? And then you can start seeing some rigidity. The answer is no. Why not? Because, again, working in the Lagrangian projection, the operation of adding certain loop smoothly. It's very easy to be done. If I take, for example, a wire here, I can do like this. And this is smoothly isotopic. We can do it also for the other side. This is smoothly, it's not forbidden, but it turns out that in the legendrian category, you cannot do this. There is no legendrian isotopy taking the straight line to the one with one loop. So the operation of adding loops has its own name. It's called stabilization. It does not change the smooth type, but it changes the legendrian class. So the following two examples are smoothly isotopic, but not legendrian isotopic. So what about higher homotopic groups? Very little was known. So at the level of pi1, it's not injective. Thomas Kalman constructed loops of positive legendrian torus nodes that are smoothly trivial, both in R3 and in S3, but legendrian non-trivial. So this is one of Kalman's loops for a trefoil. So first of all, one may pose the following question. Okay, so what does a loop in a space of embedding mean? I mean, it could, a priori, if you are not very familiar with embedding spaces, it could look a bit artificial, but you may know that in any topological space, if you have a point, then a loop is just a path starting and ending at that point. So if you are working in the space of embeddings, each point is a whole embedding itself. So what a loop is just a path of embeddings starting and ending at the same embedding. You can regard this as a movie, like for example, the one here. The two embeddings in the yellow squares are the same. So this is a path starting and ending at the same point. This path results to be trivial as a loop of smooth embeddings, but non-trivial as a loop of legendrian embeddings. The reason for being trivial as a loop of smooth embeddings is that if you take a trefoil in the torus, this loop here smoothly is isotopic to making 4 pi rotation along the torus in a rigid way. And this is this can be described by a loop of matrices acting on an embedding. And this loop of matrices lives in pi of SO3, which is C2. So whenever I have a loop of matrices given an even number of terms, it's 0 in homotopy. And since this is 4 pi, which is 2 terms, this is trivial. So if we have a trivial loop of matrices, then of course I have a trivial loop of nodes, of embeddings. So yeah, then it's not injective. But what about beyond pi1? What about pi2, pi3? The fact is that there was no understanding of this map. Very little was known, even for pi2. So what we have done is we give a precise answer for each connected component. But you have to wait a bit because first we will introduce some concepts before. Let's go with the third part of the talk, which is the homotopy type of smooth and legendrian long embeddings. I'll explain now what long means. So consider first the space M, N, Jn from S1 to S3, defined as embeddings that pass through the north pole of S3 at time 0 with derivative Jn. J multiplied by N is just quaternionic notation. So this is the picture. We have a purple embedding that, if you see here, it passes through the north pole at time 0 with a fixed derivative, which is Jn. And in the rest, it does whatever. Why is this space important? Okay, first of all, this space can be understood via the stereographic projection as the space of embeddings that are standard outside the unit cube. And by standard, we mean that it looks like the axis t, 0, 0, or reparametrization of such axis. So this is the picture. We have S3, we have a node or an embedding in S3 passing through the North Pole with fixed derivative in blue, you can see there, and you take the stereographic projection to R3. Since they pass with a fixed derivative at the North Pole, when you open this node via stereographic projection and you go to infinity, it looks almost linear. In other words, all the topology is enclosed in a compact set that at homotopy level we can take as the unit cube. Does it make sense? Okay. So this is the reason what we refer to this space as the space of long nodes. So these opened embeddings are called long. But why are we interested in these spaces? We don't want to lose track. Okay, the reason is that we can construct the following fibration. We take the space of embeddings of S1 to S3 here, which is the one we are interested in, and we project by taking gamma of 0 and gamma prime of 0, which of course are linearly independent, so they represent two linearly independent vectors in R4. Then we have an element in the Stiefel manifold for 2, which is completely understood at the level of homotopy. In fact, it's a unitary tangent bundle of S3, which is S3 times S2 or SO4 quotient by SO2. But the moral of the story is that the base space of this fibration is completely understood. The space of embeddings is the one we want to understand. And the fiber is precisely the space of long embeddings. So it suffices to understand via this fibration the space of long embeddings in order to understand the space of embeddings. And so we will focus on this space from now on. Let's fix some notation first. So denote by diff of D3 the group of diffeomorphisms of the 3 disk relative to a certain open neighborhood of D3, meaning that they fix the neighborhood of the boundary, and given gamma long node, denote by embedding super gamma its connected component. This is just notation. But interesting fact here is that the space of diffeomorphisms of the 3 disk naturally acts in the space of each connected component of long embeddings. Why is that? Because, as we said, they fix a whole open neighborhood of the boundary. So if you take any long node, it will remain being a long node with fixed position and derivative at time 0, and then it does whatever. And so what's the stabilizer? Oh, sorry. Okay, just a second. I don't know what happened. Yeah, I don't know why it lost the connection.
Don't worry, John. Just
Okay.
take your time to fix it.
Okay, if you can maybe stop the recording, I don't know.
No worries.
Okay, thank you. What's the stabilizer of gamma? Yeah, maybe with this interruption, I'll make a very brief recap. We had the space of diffeomorphisms of the 3 disk. We said that it actually naturally acts in the space of long embeddings in each connected component. Oh, sorry. Yeah, maybe it was the battery of my laptop.
Okay. Could you just say one more time what embeddings are called long? Just briefly.
Yeah, for sure. Because as we mentioned before, they can be understood via the stereographic projection with this kind of picture where it's very long, going to infinity in a linear way. Does it make sense?
Yes, thank you.
You're welcome. So I was saying that you have the diffeomorphisms of the 3 disk fixing an open neighborhood of the boundary. They act on space of long nodes and its connected component. What's the stabilizer of gamma? So it turns out to be the group of diffeomorphisms of the node complement, which is S3 minus an open neighborhood of the node. And we denote it by diff of C gamma. So we have the following locally trivial fiber bundle. Again, just not to lose track, we are interested in understanding the topology of the space of embeddings. Then this turns out to be easier maybe to study the homotopy type of long embeddings. And via this vibration, what we get is that it suffices to study the group of diffeomorphisms of the complement. According to Hatcher, the group of the diffeomorphisms of the complement is homotopically discrete. And it turns out to be that the space of long embeddings in the smooth category is very well understood. It's a KG1, which means that it has G as fundamental group depending on the connected component, and the higher homotopy groups vanish. This is work by Hatcher and Badney. I put some examples here. For the unknot, which is a certain kind of knots, G is 0, the trivial group. For torus knots, it's C. Let's go now with the legendrian picture. Okay, we can translate this discussion above to the contact setting. If we denote by leg and JN, just long knots, but which are at the same time legendrian, we can replicate the same discussion. So let's go by parts. In the first square here, we have the vibration that we recently saw, that it's you take embeddings, you project down to the Stiefel manifold, and you get the fiber, the space of long embeddings. But it turns out that now here in the legendrian setting, you can do the same. You take a legendrian, you project down to gamma, gamma prime, that turns out to be in U2, which is also very well known in terms of homotopy groups. And so the fiber is the space of long legendrians. But again, if you go to the legendrian vibration that takes, okay, the diffeomorphisms of the 3 disks fixing the neighborhood of the boundary, you project to the space of connected components of long knots with fiber, the knot complement, the diffeomorphisms of the knot complement. Again, you replicate this discussion in the contact category, and you get contactomorphisms of the 3 disk fixing an open neighborhood of the boundary projects to the connected component of long legendrians, and you get the fiber, the contactomorphism group of the knot complement. And everything works. The funny thing here is that you get this, this chain of vibrations. And just note that the central column, the one concerning contactomorphisms and diffeomorphisms of the 3 disk fixing the neighborhood of the boundary, they are both contractible. The one of contactomorphisms is due to Eliasberg's work, and the one of diffeomorphisms, it comes from Hatcher, from the positive answer to the Smell conjecture. So, since both are trivial, it turns out that understanding this part tantamounts to understanding this other part. And so one of the results that we get, and that Eduardo may explain in more detail, it's that, in fact, the left column, the contactomorphisms of the complement inside the diffeomorphisms of the complement, I didn't say it, but okay, it's clear that the first row goes down to the second row just by the natural inclusion of the legendrian or contact diffeomorphisms inside the smooth counterpart. And as a consequence, we can answer the big question that we were posing in the beginning, which is the inclusion of long legendrians inside the space of long embeddings is a weak homotopy equivalence. In fact, we can describe the space of legendrians, not long, but legendrians from S1 to S3 as a product, which is U2 times the KG1, the one arising from the smooth topology, and which is computed by Hatcher and Badney. Hatcher computed some connected components, and Badney carried out the whole classification. So theorem 1 will be covered in the second session by Eduardo Fernandez. And so he will give more details than I did. And so thank you very much for your attention.